The Max Planck was a scientist who studied on the particle nature of electromagnetic radiation, and he discovered the phenomena of blackbody radiation. Blackbody is a body which can absorb or emit the radiation of all frequency. What is the threshold frequency? It is the minimum frequency which is required to eject the electron. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Structure of Atom. Under that, we also discussed about the Maxwell theory of electromagnetic radiation, and we discussed about the electromagnetic spectrum. Today, let us move on to the next topic of this unit about the Planck's constant and the photoelectric effect. First, we will see what is the Planck's constant and who discovered this Planck's constant. Let us understand first. The particle nature of electromagnetic radiation was first studied by Max Planck, and the first concrete explanation for the phenomena of blackbody radiation was given by the Max Planck in 1900. So remember, the Max Planck was a scientist who studied on the particle nature of electromagnetic radiation, and he discovered the phenomena of blackbody radiation. Now let us understand what is that blackbody radiation. According to the Planck's quantum theory, the body which emits or absorbs the radiation at all frequency, they are known as blackbody radiation. According to the Max Planck, he says that blackbody is a body which can absorb or emit the radiation of all frequency. Once it absorbs the radiation, it will emit the radiation. So it can absorb the radiation of all frequency, hence it is known as a black body. And the radiation which are emitted by this body are known as black body radiation. After absorbing, the radiation must be get emitted. So the emitted radiation from this body, they are known as a black body radiation. They are known as black body radiation. So this phenomena of blackbody radiation was first studied by the Max Planck in the year 1900. So what is the black body here? The black body is a body that can easily absorb the radiations of all frequency. Once it absorbs the radiation of all frequency, which can easily get emitted. The radiation which is get emitted from this body, they are known as a black body radiation. Now, let's see how does he explain this concept by using this black body radiation. The extra frequency of distribution of the emitted radiation from the black body, which is always depends upon the temperature. He says that the frequency distribution of the emitted radiation from the black body is always depends upon the temperature. The emitted radiation from the black body is always depends upon the temperature. At a given temperature, the intensity of radiation emitted is increases with the decreasing in a wavelength. Here, he plot the wavelength versus intensity. So, when he observed that, this graph, he observed that the intensity of the radiation which is get emitted from the black body, which will be increases, then it will be decreases with the wavelength. You can see here, first it will be increases, then it will be decreases. Similarly, it is first increases, then it will be decreases. And reaches the maximum value at the given wavelength, and then start will be decreases with the further decreasing in the wavelength. So this was a phenomena was first explained by the Max Planck. Remember, the Max Planck is the one who explained the concrete phenomena known as a black body radiation. The black body radiation means it can easily absorb the radiation of all frequency. When you plot, we come to know that this absorbed frequency or the emitted radiations, which is always directly proportional to the temperature. That is why the intensity of the radiation is plotted against the wavelength. When you plot the graph, you can easily observe that the emitted radiations will be started increasing, later it will be decreased with a decreasing in the wavelength. This was a first observation was made by the Max Planck, and the Planck could explain the distribution of intensity in the radiation from the black body as a function of frequency at a different temperature. To explain this, he gave some of the postulate. Now let us see which are the postulate was given by the Max Planck to explain that the frequency of the emitted radiations, which also depends upon the temperature. According to him, the atoms and the molecules could emit or absorb the energy in a small discrete quantity. They are known as photon. According to him, the atoms and the molecule which can easily absorb or emit the radiation in the form of small discrete packets, they are known as photon or quanta. And in the second postulate, he says that the energy of the quanta of radiation is always proportional to the frequency. So once the atoms or the molecules, once it absorbs the energy in the form of packets, they are known as a quanta, which emits on this quanta, which is directly proportional to the frequency of radiation, and he know that the energy is directly proportional to the frequency, and in order to remove this proportionality constant, he put a new letter known as H, and it can be defined as E is equal to H mu, where H is a Planck constant and it is always having the constant value called 6.626 into 10 to the minus 34 joules per second. This is how the Max Planck, in order to relate the distribution of intensity of radiation from the black body as a function of frequency, he put this all the three postulate. According to the first postulate, it states that when atoms or the molecule, once it absorb the energy absorbed energy will be in the form of small discrete packets. They are known as quanta or photon. And this energy which is present inside this quanta or the photon, which is directly proportional to the frequency. That is why I have written E is directly proportional to the frequency. In order to remove that proportionality constant, he put a letter called as H, where H is known as a proportionality constant and E is the energy and mu is nothing but a frequency. Understood? And the H will always having the constant value, that is 6.626 into 10 to the minus 34 joule per second. Now, the energy is always emitted is a integral multiple of H mu. That is why he gave another formula, that is E is equal to N into H mu. When the energy get emitted, it will become a integral multiple of H mu. So, E is equal to N into H mu, where N is a integer. This is how, when the black body absorbs the energy and it emits the radiation, that relationship he stated by using the three postulate. Hope you all understood with the derivation which has been done by the Max Planck by using the black body radiation concept. Now, let us move on to the next topic, that is photoelectric effect. Albert Einstein used the Planck's quantum theory in the 1905 to explain the photoelectric effect. After the discovery of the Planck's constant, the Einstein, he started doing his work based upon the photoelectric effect and he put forward the photoelectric theory also. Let's see what is that photoelectric effect now. The phenomena of ejection of electron from the surface of the metal when the light of suitable frequency is strikes. That is known as photoelectric effect. And the electrons will be get ejected. They are known as photoelectron. Here you can consider this is as a metal surface. Okay. When the light of suitable frequency which is allowed to strikes on this metal surface, obviously the electrons will be get ejected. This phenomena which is known as photoelectric effect, and this ejected electron, they are known as photoelectron. They are known as what? Photoelectron. Here the photo, it refers to the light. By using the light, you are ejecting the electron, hence it is known as photoelectric effect. Hope you are understood with the concept. It is very simple. He used the light to eject the electron on the metal surface. What does he use? He used the light of suitable frequency which is allowed to strikes on the metal surface so that the electrons will be get ejected. So this phenomena which is known as photoelectric effect, and electrons are ejected, they are known as photoelectrons. Now, for this also have given the experimental result by using this photoelectric effect. So when the beam of light which is falls on the metal surface, the electrons will be get ejected immediately. So here I have taken the glass tube. Inside this glass tube, it is nothing but a vacuum chamber, and have placed the metal surface. When the light of certain frequency which is allowed to fall on this metal surface, the electrons will be get ejected, and later it will be detected by the detector. The number of electrons which is get ejected, they are directly proportional to the intensity or the brightness of the light. When number of electrons are get ejected, they are directly proportional to this intensity of the light. And in the third observation, he says that the minimum frequency of incident radiation for which photoelectric effect will be just taking place, they are known as threshold frequency. What is the threshold frequency? It is the minimum frequency which is required to eject the electron or to conduct the photoelectric effect. They are known as threshold frequency. If the frequency of the light is lesser than the threshold frequency, and there will be no ejection of the electron as long as if you pass the light on the metal surface. These are the 4 important observations was made by the Einstein in his photoelectric effect. What does he explain? In this entire setup, he used the vacuum chamber. Inside this vacuum chamber, he placed the metal surface, and also there is a detector. When the light is suitable frequency which is allowed to fall on the metal surface, what will happen? The electrons will be get ejected. These electrons, the ejected electrons will be get detected by the detector. And in the same experiment, he says that the number of electrons get ejected, they are directly proportional to the intensity of light. And for this, to conduct a photoelectric effect, we need a minimum frequency of light, or the minimum intensity of the light is required to conduct the ejection of the electron, to conduct the photoelectric effect, that is known as threshold frequency. If you don't use the suitable frequency to eject the electron from the metal surface, there is no use and there is no photoelectric effect will be taking place. So that he used another phenomena called as work function. It is nothing but a minimum energy required to eject the electron, and it is also known as photoelectric work function, and it can be denoted as W naught, which is equal to H into mu naught, where H is a Planck constant and mu naught, which is nothing but a threshold frequency. What is the threshold frequency here? It is a minimum frequency of light which is required to eject the electron. Understood? And energy of ejected electron can be obtained by H into mu naught, which is equal to half mv square, where H is a Planck constant, V is the frequency of radiation, and mu naught, which is nothing but a threshold energy, and me is the mass of an electron. Again, mu is nothing but a frequency of the radiation or the velocity of the radiation with the ejected electron. This is how Einstein uses the Planck's quantum theory to explain the photoelectric effect, and this formula and this one we usually use while solving the numerical, and this equation, which is also known as Einstein photoelectric equation. Hope you all understood with this equation how we got and how does he explain by using the frequency of suitable radiation to pass on the metal surface to eject the electron. Now let us solve some of the numerical. Okay. Calculate the energy of 1 mole of photon of the radiation whose frequency is 5 into 10 to the power of 14 hertz. Here they have given the mu, that is a frequency value of the photon they have given, that is 5 into 10 to the power of 14 hertz. Here we need to calculate the energy of the 1 mole of the photon. We know that energy which is given by h into mu, and we know that h is nothing but a 6.626 into 10 to the power of minus 34 joules per mole. Is it right? This is a constant value and it is known as, it is a Planck's constant. So 6.626 into 10 to the power of minus 34 into, what is the mu value here? So 5 into 10 to the power of 14 hertz. So if you multiply these two, 3.313 into 10 to the power of here minus 34 and 14. So plus into minus, so it is 20. So if you replace the decimal point, it will become 10 to the power of 19 and it will become minus 19. This is how we can calculate the energy of the photon. But they have asked you to calculate the energy of 1 photon. We know that 1 mole, which is always equal to 6.623 into 10 to the power of 23 joules per mole. Now, in order to calculate the energy of 1 mole of a photon, we need to multiply the value of 1 mole with this value of the energy as we obtained. So, E is equal to 1 mole value 6.623 into 10 to the power of 23 into the value as we obtained from the multiplications of the Planck's constant with the frequency, that is 3.313 into 10 to the power of minus 19. 10 to the power of minus 19. If you multiply these two, 1.995 into 10 to the power of 5 joules per mole. This is how we can easily calculate the energy of the 1 mole of photon by using the frequency. In the first step, I have written the given frequency. In the next step, I have calculated the energy by using the Planck's constant along with the frequency. After knowing this, the energy of the photon, we need to calculate the energy of 1 mole of the photon. We know that 1 mole, which is always equal to 6.623 into 10 to the power of 23 joule per mole. So, I have substituted this value to the above equation and I'll get 1.99 into 10 to the power of 5 joules per mole. Hope you all understood with this. Now let us solve the another problem. That is, when electromagnetic radiation of wavelength 300 nanometer falls on the surface of the sodium, the electrons are get emitted of the kinetic energy 1.68 into 10 to the power of 5 joules per mole. What is the minimum energy is needed to remove an electron from a sodium, and what is the minimum wavelength that will be causes the photoelectric effect, photoelectrons to get emitted? Here they have given the lambda, that is a wavelength, that is 300 nanometer. So we need to convert into the meter, that is 300 into 10 to the power of minus 9 meter. Okay, and also they have given the kinetic energy, that is 1.68 into 10 to the power of 5 joules per mole. After knowing this data, now we need to calculate the energy of the radiation. We know that E is equal to h mu, where mu is equal to C divided by lambda. So h C divided by lambda, we know that h is equal to 6.626 into 10 power of minus 34, and for the velocity of light, which will be equal to 3 into 10 power of 8 meter per second, and the lambda, which is also given. So substitute this value 6.626 into 10 power of minus 34 into 3 into 10 power of 8 divided by 300 into 10 power of 9 minus 9. If first you solve these two, that is minus 34 plus 8. After that, then add a plus 9. So how much you'll get the answer for this? You will get 626 into 10 power of minus 19 joules. 10 power of minus 19 joules. Here they have not given the frequency. That is why I have used the relationship with the velocity with the frequency. Okay. So that is why I got the energy, that is E is equal to 6.626 into 10 power of minus 19 joules. Now, we need to calculate the minimum energy required to remove the one electron from the sodium. We know that they have given the kinetic energy. So, first, the energy of one photon, 1 mole of photon is given by multiplying this value with the Avogadro number, that is 6.626 into 10 power of minus 19 into 6.623 into 10 power of 23 joules per mole. If you multiply these two, you will get 3.99 into 10 power of 5. 3.99 into 10 power of 9. So this is the energy of the 1 mole of photon. After knowing this value, we need to calculate the minimum energy required to remove the 1 mole of sodium. See here they have given the kinetic energy. So energy required to remove the 1 electron means E is equal to energy as we obtained minus kinetic energy. That is 3.99 into 10 power of 5 minus kinetic energy is 1.68 into 10 power of 5 joules per mole. 2.31 into 10 power of 5 joules per mole. After knowing this, energy is required to remove the 1 mole of an energy is required to remove the 1 electron from the sodium. We need to calculate the maximum wavelength of the photoelectron to be get emitted. So after knowing this energy, minimum energy of an electron to remove that 1 proton was given by dividing this value, that is the E value, divided by here. After knowing that energy of the, by subtracting the energy as we obtained minus kinetic energy, we got energy is equal to 2.31 into 10 power of 5 joules per mole. After knowing this, we need to calculate the minimum energy required to eject the 1 electron from the sodium. How to get this? We know that J is equal to 2.31 into 10 power of 5. To eject the electron, we know that 6.022 into 10 power of 23 moles, that is a 1 mole of photon. So that it will be equal to 3.84 10 power of minus 19 joules. So you are dividing this value divided by Avogadro number. So it is 3.84 into 10 power of minus 19 joules. After knowing this, next we'll see with the maximum wavelength to eject the photoelectron. Lambda is equal to hc divided by E. We know that E is equal to hc divided by lambda. Here we got the relationship, that is a lambda we have got, that is 3.8. We need to calculate the energy, we have no, we need to calculate the lambda. So that is 6.626 into 10 power of minus 34 into 3 into 10 power of 8 divided by this energy value is 3.8 into 10 power of minus 19. If you solve this, you will get 517 nanometer. So 517 nanometer, and it is corresponding to the green light. So this shows that to calculate the minimum wavelength by using the energy also we can calculate, and also they have given the kinetic energy. I have subtracted the energy as we obtained minus kinetic energy. So we will get the final answer as 517 nanometer. This is how we can easily solve the numerical based upon the Planck's constant as well as the photoelectric effect. So in the next session, we are going to understand with the atomic spectra. By this, I like to say that whatever we discussed in this session, it is very important for the examination point of view. Please have a look on it and try to solve the numericals which is given on your NCERT textbook. Till that, take care and be safe. Thank you.